All right, guys. Hi again. I want to try to complete the Routh-Hurwitz technique. In fact, Dr. Emre Özkan also has put out a solved example, which is a bit more complicated than our initial examples. So let's try to finish what we started. Okay, so Routh-Hurwitz continued. In fact, the last example that I had written on our notes, I had solved it on our lecture on Wednesday, but not all of you have actually participated in that lecture, so I want to very quickly solve it again. And I hope you guys that you were also able to solve it by yourself. Okay, so we had a fifth order polynomial. Okay, and I'm writing it again. Okay, so let's take a look at the initial checks. Okay, so no sign changes in the polynomial. Okay, which would have directly indicated that we have an unstable system, and also no coefficient vanishes. So these are the initial checks. Okay, if any one of these initial checks fail, you can at least immediately say that your system is unstable, but you cannot make further conclusions unless you really go with your route array. So let's calculate our route array: S5, S4, S3, S2, S1, and S0. So these are our rows. The first two rows, as we said, is from our polynomial. So we will start with coefficient of S5 is 1, coefficient of S4 is 1. Then I have a 2, then I have a 1, 1, and 1. And the rest of the coefficients you can do not exist, so they will be taken as zeros. Okay, so let's take a look at the first entry over here, right? So it's gonna be 1 by 2 minus 1. Okay, so 1 by 1, sorry, 1 by 1. Okay, so 1, 1, sorry about that, 1, 2, minus 1 divided by 1. Okay, so that's going to be simply 1. Okay, so this is our first entry over here. Similarly, 1 by 1, which makes 1, minus 1, 0 divided by 1, which is a 0, and the rest also 0 because it's all multiplications by zeros over here. Okay, let's take a look at the next row. Okay, so this is 1 minus 0 over 1, which makes a 1. 1 minus 0 over 1, which makes another 1, and 0. And the next row is 1 by 0, which makes 0, minus 1, makes minus 1 over 1, which makes a minus 1. The rest of the coefficients are 0. And finally, I have minus 1, minus 0 over minus 1 makes a plus 1. Okay, so that's our route array. So what is our conclusion? Our conclusion is based on the first column. So we mark the first column. How many sign changes we have is that we have one sign change here, another one sign change here. So we have two sign changes. Obviously, in the first column is what we are looking at. So we have system being unstable, and we have two unstable poles. Unstable meaning right half plane poles. Okay, so that is how we can use the route array to talk about our system stability. Okay, and mind you that this, I call this d of s, but this is in fact our characteristic polynomial, right? Characteristic polynomial. That means I need to first found the closed loop transfer function. Okay, so with the numerator of s over denominator of s. So the denominator is what we are analyzing in the Routh-Hurwitz method. Okay. All right. So now let us go to now when we are doing this, okay, there may be some difficulties. In fact, some numerical difficulties. Okay, numerical difficulties with the difficulties with Routh-Hurwitz technique. We have two cases with this. Case one, we can call this a 0 in the first column. Now, if you remember the technique, we at each calculation, we are actually dividing by an entry in the first column. So if we end up having a 0 in the first column, that results in a division by 0, and that has to be taken care of. Okay, division by 0 problem. Okay, so let me give you an example. So let us consider, for example, that our denominator polynomial is with a repeated pole at +1 and another pole at -2. Okay, so let us expand that, and that's going to turn out to be s cubed minus 3s plus 2 equals to 0 is the equation that we need to find the roots for. Okay. Now, if you take a look at the basic test, okay, we basically have a sign change in coefficients. So you can automatically say that the system is unstable, but you cannot make any further conclusions, okay? Because one of the tests fail, it is automatically concluded that we have an unstable system. And in fact, we can see that because we have a repeated pole at +1, okay? So let's now take a look at what happens with the Routh-Hurwitz array, okay, or the route array. Okay, so let's see whether we can continue with the route procedure in order to find out how many poles are on the right half plane. Okay, so we have s cubed, this is a third order polynomial. So we have 4 rows. The first 2 rows are from the polynomial, but you need to be careful. You see that we have the s square term missing here. So we have a 0 coefficient. Okay, so let me put down the coefficients. S cubed has a coefficient of 1. S square has a coefficient of 0. Then we have -3, and we have 2, and the rest of the coefficients can be taken as 0. Okay. Now the 0 in the first column can arise directly from the given polynomial, or it can be a result of a calculation. So you can have, for example, a 0 first column in the S1 row as well. Okay. So now when I try to calculate this entry over here, obviously I have 0 times -3, -2, but then divided by 0, and that means that I cannot calculate this value. Okay. So the question is how we can apply the Routh test. How can we proceed? With this difficulty, there are actually three different ways that you can fix this problem. Three approaches, and I'm going to give examples for each. Okay, three approaches to fix this difficulty. Let me first list them. One of the approaches is that you can replace the s variable by another variable, which is 1 over z. Okay? Another variable. Now note that having s replaced by 1 over z, meaning s equals 1 over z, does not change the result that we are looking for. Okay? Any pole of the original polynomial that is on the right hand side will also be a root of the polynomial of what we are when we replace s by 1 over z, because this change of variable does not change the sign of the pole. It just modifies the magnitude of the pole. Okay, so the sign remains the same. Therefore, with respect to the left half or right half plane, the result does not change. Okay, so this change of variable this change of variable does not change the result we are looking for. Okay. Another approach is actually adding to the polynomial a root that we know what it is. Okay, so we can multiply the given polynomial q of s by s plus alpha, where alpha is known. So depending on where alpha is, you will either increase the result you are looking for. For example, if alpha is an unstable pole, in that case, the result that you will get will be one more than what is the unstable poles of the original polynomial. Or if alpha is on the left-hand side, a stable pole, then you will not change the result that you are looking for. Okay? So, analyze the new polynomial. Let's call this q prime of s, which is equal to q of s times s plus alpha. Obviously, you will expand this to find the new polynomial q prime of s. Okay, and the final approach is you replace the offending zero by a small constant epsilon. Okay, then let epsilon goes to 0. A slight perturbation of the original system. Obviously, you can assume epsilon to be positive or negative. Normally, your result should not change, okay? Because the perturbation can be either way of that 0, okay? So let me solve some examples with that, okay? So let me, for example, consider the first approach. Okay, so consider A with our original problem, right? Q of S is equal to S cube minus 3S plus 2. Okay, so let us calculate Q prime of S. Okay, okay, sorry about that. Q prime of Z, okay, where I will replace every S with 1 over Z. So this will be 1 over Z cube from S cube minus 3 times 1 over Z plus 2, and I'm going to equate this to 0 to solve the new polynomial in Z. Okay, so obviously because this is equated to 0, what I can do is I can equate the denominators to find the numerator, and then the numerator will be equal to 0 in order to make the polynomial equal to 0. Okay, so that's going to be 1 minus 3z square minus 3z square plus 2z cube over z cube. Okay, so equal to 0, and that would mean that I have 2z cube minus 3z square plus 1 is equal to 0. So now I have a new polynomial in Z, and I can apply the Routh-Hurwitz method to this new polynomial. Okay, so let's try to do that. We have a third order polynomial, z cubed z square z1 z0, and I have the first two rows from the given polynomial, so I will have 2 as my first entry minus 3, then I have a 1, 0 and 0 and 0. Okay, so let's make our calculation. So this is going to be minus 3 times 1 minus 3 minus 0 divided by minus 3. So it's going to be minus 3 times 1 minus 0 divided by minus 3. Okay, so I have a mistake here. Obviously I have a mistake because you see what was my mistake. This polynomial is z cubed z2, a missing coefficient at z to the power 1. So in fact I have my coefficients wrong, so I'm going to correct that. Okay, so 2 minus 3 is fine, but this is wrong. So I'm going to have to correct all of this. So that's going to be a 0 here, and then a 1, and then a 0 and a 0. Okay, so this is a common mistake, basically forgetting about a missing coefficient in the route array. So be careful with that. Okay, so this is minus 3 times 0, minus 3 times 0, which is 0, minus 2 divided by minus 3. So this is minus 2 over minus 3, so it's going to be 2 over 3 over here. The rest is a 0 coefficient. And over here I have 2 over 3 times 1 minus 0 over 2 over 3, so I'm going to have a 1 here. So now let's take a look at the sign changes. Okay, so the first column is here. I have one sign change over here, another sign change over here, and then a total of 2 sign changes. Okay, so 2 sign changes, meaning system unstable with 2 unstable poles. Okay, now we already knew that this was the case because if you remember, this polynomial that we had was in fact composed of s minus 1 square times s plus 2. So you see that we have over here two unstable poles in the original system. Okay. All right. So please don't forget to log in your questions in the dedicated forum so that we can try to answer them when we have an interactive session. Okay. Now let us take the same example, but now with the second case. Okay. So now consider fix B. Okay. So what we will do is we will again take the same polynomial, okay, which was s cubed minus 3s plus 2. But what I will do is that I will multiply this polynomial by s plus 3. This means a pole at s is equal to minus 3. So this is a stable pole at left half plane. So what we expect is that this will not change the number of sign changes, because that's going to give us the number of poles in the right half plane. Okay, so we expect that the resulting new polynomial, which is going to be of fourth order now, will have to have only two sign changes if we don't end up with the same kind of difficulty. Okay, so let us calculate our q prime of s, which is going to be the multiplication of this two. So that's going to be s4 minus 3s squared plus 2s from multiplying s with this polynomial. And then the terms coming from the multiplication of 3 with this, plus 3s cubed minus 9s and then plus 6. Okay, so let's rearrange the terms. We have s4 minus 3s squared. So minus 3s squared. Is there any other? Okay, so that's going to be plus 3s cubed. No other s squared terms, minus 3s squared. And then here actually I have 2s minus 9s, so I will have minus 7s. Okay, these two terms come together to give us minus 7s and plus 6. So this is our new polynomial. So let's try to construct our route array. I'm going to have S4, S3, S2, S1, S0. And I have S4, S3, S2, S1, S0, no missing coefficients here. So but there are sign changes obviously indicating that I have an unstable system. So I'm going to have 1, 3, minus 3, minus 7, 6, and 0. Okay. So here, for this term, I have 3 times minus 3, minus 7 over 3. Okay, so this is minus 9 plus 7, so it's going to be 2 over 3. Sorry, minus 9 plus 7, so it's going to be minus 2 over 3. Minus 2 over 3. Okay, so I'm going to have minus 2 over 3 in this entry. Then I have 3 times 6 minus 0 over 3. So I will have 6 over here and then zeros for the rest of the terms. Okay. Now what about this term? So this is going to be minus 2 over 3 times minus 7 minus 3 times 6 over minus 2 over 3. So I'm going to skip the details of this calculation, but you should get 20 if I'm not mistaken at this entry. The rest of the terms are again 0. Okay. For the last entry, this is going to be 20 times 6 minus 0 over 20, so you will get 6 on this last entry. Okay. Again, first column, there is one sign change here, another sign change here, 2 sign changes, and we have the same result. Okay. Now, what if I had multiplied the polynomial by a term that corresponds to an unstable pole? Just for for completeness, I will also cover that. So instead of s plus 3, I will this time multiply it by s minus 2, which should increase this number of sign changes by 1 because we are adding an unstable pole. Okay. What if we multiplied by s minus 2? We should increase the number of sign changes by 1. Okay, so that's our expectation. So let's see whether that holds. Okay, so here q prime of s will be equal to the multiplication of s cubed minus 3s plus 2 multiplied by s minus 2. So that's going to give us again s4 minus 3s squared plus 2s. Now multiply minus 2 by this, minus 2s cubed plus 6s and minus 4. So that's gonna come out as s4. You have only one s squared term, 3s squared, then plus 2s plus 6s. So you will have, sorry, I forgot about the s cubed term. Sorry about that. So let's minus 2s cubed minus 3s squared plus 2s plus 6s plus 8s, and we have minus 4 as our last term. Okay. Let us construct our route array. So we have S4, S3, S2, S1, and S0. So we have 1, minus 2, minus 3, plus 8, minus 4, and 0. Okay. So let's see what happens. So we have minus 2 times minus 3, minus 2, minus 3, minus 8 divided by minus 2. So that's going to be plus 6 minus 8. So minus 2 over minus 2, that's going to be a 1. Over here, minus 2, minus 4, minus 0 over minus 2. So I have minus 4 here. Okay. And 0 for the rest. Let's take a look at here. It is 8 minus 8 minus 2 times minus 4. So that makes another 8 over 1. Basically, we have another 0 here. Okay. So this trial did not fix our problem. That is a possibility. Did not fix our difficulty. But remember, you are completely free to try whatever route that you want. So that trial did not work, so you can try another one. For example, try s minus 1. Again, this is an unstable pole. In this case, q prime of s will be equal to s4, and I leave to you the calculation. Minus s cubed minus 3s squared plus 5s minus 2. Okay, so that's the resulting polynomial. So if we move on with that polynomial, so I'm gonna have s4, s3, s2, s1, s0. Okay, and we have 1, minus 1, minus 3, 5, minus 2, and 0. Okay. In this case, if you do the calculations, minus 1 minus 3 makes 3 minus 5. So minus 1 minus 3 minus 5. So this becomes 3 minus 5 minus 2 over minus 1. That's going to be equal to 2. So we have a 2 here. Minus 1 minus 2 makes 2. Minus 0 over minus 1 makes a minus 2. Okay. So, and 0 here. Let's take a look at the next row. 10 minus 2, which makes an 8 over 2. That makes a 4 over here. And 0, 0, we have 0 here. And finally, we have 4 times minus 2, minus 0 over 4. So I have a minus 2 here. Okay. So as expected, this unstable pole that we have added actually has increased the number of sign changes. So you see I have one sign change, is another sign change here from these terms, and then over here another final sign change. Okay, so I have 3 sign changes as expected. But careful, okay, still 2 unstable poles of the original Q of S. Okay, so please don't forget that you have added the third one. It wasn't originally there. Okay, so it's you have to be careful not to count the one that you have added as being an one of the original poles. Okay, so let me see. So this is half an hour. So let me divide the video for the last part for you.